not that way.
All right, it's 3:05, so let's get started. So, who hasn't been here? Who hasn't been to recitation yet? Okay, so new people. So, on the course webpage, we have solutions to quiz 1. So, a lot of people struggled with 2 of the questions, so I would really recommend looking at those solutions. I also posted solutions to all the exercises we did last week. So make sure to take a look at those, and homework 1 is out. The first part is due, I believe, Saturday night at midnight, and the second part is due a week from then. So are there any questions before we get started? No questions? All right, so what was the main thing we talked about last week? What was the main thing that we were able to prove?
The language is regular, accepted by DFA.
Well, that was the main definition we came up with, but what was the main thing that we looked at in terms of the languages of DFAs? Well, first of all, what is a language? It's a set of what? A set of strings, right. So, what is the first thing you want to do if you have 2 sets? Stare at them and hope something pretty will come out of them, right? Well, what's the first thing you want to do with DFA? With languages. If I have 2 sets together, how would I combine them together? Union, right? I put these 2 sets together. Well, what's another operation we might want to do putting 2 sets together? Intersection, right? So let's think of these 2 operations again. Oh, what was that third operation we talked about?
Complement.
Complement, yeah. So take everything that's not already in the set. And what was the main thing that we were able to realize about these 3 operations? That they have nice names. Really, what was the main thing we saw with these 3 operations? This close thing. So what does that mean? It means that if I have 2 regular languages and I put them together either with union or intersection, I still get a regular language. What about complement? If I take any regular language, find the complement of that language, so everything in sigma star that's not in that language, that's also regular. And so how were we able to see this complement? How were we able to show that languages are closed, regular languages are closed under complement? So what did we modify to the machine?
Find it stage.
Yeah. So if I have a DFA with some final states, then if I swap the final and non-final states, then I get a DFA for the complement. And why is that true? Because there's only one computation for a given string. So that must mean wherever it ends up is in a final or non-final state. So if it was in, say, a non-final state, if I swap the final and non-final states, I now get a DFA for the complement of the original language. So that's how we were able to show that. But what about these 2? How did we show these? So what was the name of the construction that we used? Maybe it'll be more apparent if I give an example. So I have 2 DFAs, M1 with states Q1, some alphabet, transition function, start state, set of final states. And I have M2, some other states, alphabet, some transition function, start state, final states. And so now, I want to make, let's just do union first. So I want to make a DFA that is the union of these 2, the languages of these 2 machines. So how did we actually do that? Well, one idea that will work is I just look at the first machine, whatever input I have, feed it to the first machine, and then also feed it to the second machine, and then see what they say. Oh, I'll get to that. Okay. So why would my idea not work? Feed it to the first machine, then feed it to the second, and then accept if at least one of the two accepts.
Your input.
Oh, the input goes away. So that's the problem. So the suggestion was, let's try to look at some kind of relationship between these two DFAs, and then try to put them so that I only read the input exactly one time, which would be really nice. So let's do that. Let's make a machine M with some states. So how do I look at both machines at the same time? Quote unquote, run them in parallel. How would I do that? Or how did we do that? Oh, it's the ordered pair thing that we talked about, right? So I'm going to keep track of two things at the same time. The first one is the state I would have been in the first machine, and the second coordinate is where I would have been in the second machine. Okay, well, how do I look at all the possible... Is that a firewall?
Not in here.
Not in here, we're fine. So, how do I look at the set of all possible ordered pairs between these two sets?
Using the transition table.
I'm looking at states only. All possible choices of things from Q1, and then all possible things from Q2.
So Q1 cross Q2.
Ah, yeah, Cartesian product, exactly. So Q1 cross Q2. Right? This is the set of all possible ordered pairs where the first guy comes from the states of the first machine, second guy comes from the states of the second machine. Pretty simple. I think the alphabet is going to be the same, so I'm not going to change that. I'm going to have some transition functions that I'm not going to specify just yet. So let's try to reason about what the start state of this new machine is. So I'm going to ask this several times as we're doing this. What are the states of this new machine? What are the names of the states of this new machine? 2 words. Ordered pairs, right? This is a set of ordered pairs. So the start state better be an ordered pair, right? Because it's the state of the machine. So I'm going to call it an ordered pair. But how do I find out what goes in each of the 2 coordinates? How do I figure that out?
Well, you're given the start station.
Ah, I look in the original machines and I figure out, okay, those are my 2 start states. That's going to be the start state of this new machine. Just put this guy in the first coordinate, this guy in the second coordinate. So Q01, Q02. And then I'm going to figure out what the final states are in a second. Good so far? Sweet. So let's figure out what the transition function is. So what is the transition function of a DFA take as input? What are the 2 things it takes? Ah, yeah, the state that we're currently in and the symbol that we're reading. Again, what are the states of this machine? Ordered pairs. Nice. So the first thing of this transition function, the first argument, better be an ordered pair. So I'm going to call it Q1, Q2 to be my ordered pair. And the symbol that I'm reading is some character A. Well, what is the transition function output? Again, what are the states of the machine? Ordered pairs. So I better output an ordered pair, right? So I'm going to output an ordered pair. Okay, well, I have 2 things to put in this ordered pair. How do I find out what to put in each of the 2 pieces? Well, what is the first coordinate keeping track of? What state I would have been in the first machine. So So this guy better be in the state I would have been in the first machine. Wait, how do I find that out?
Transition variables.
I look in the transition function of the first machine. Oh, what state was I in of the first machine? It's not a rhetorical question. What state was I in the first machine? Q1. So I look up in the first transition function with Q1 and A, and that's where it takes me. Don't worry, we have plenty of examples, but it's important to know that the first coordinate is keeping track of where I would have gone in the first machine. And what do you think the second coordinate is going to be?
Q2.
The transition function 2 with Q2. So function 2, Q2, there. Good so far?
Yeah.
Question for you. Did anything I've done so far have anything to do with the word intersection or union? So what changes if I used union or intersection? The final states. So let's figure out what the final states are. Well, what are the final states? Well, what kind of thing is it? It's the something of final states. Starts with an S. Set. So I better write down a set. Again, what are the states of the machine? Ordered pairs. So I better write down a set of ordered pairs. So I'm going to again write Q1, Q2 to be the ordered set of ordered pairs. And then now we got to distinguish: are we doing union or intersection? So let's say we're doing union. So what do I need to know about Q1 and Q2 in order to do union? Well, what criteria have to happen for this to be a final state of the new machine? Well, which one has to accept? Both or what?
For union either.
For union, how many do it have to accept? At least one of them, right? Because if Q1 accepts, then that must have meant that the first machine accepted, which means it's in the union. If it's the second machine that accepted, then we're good. If it's both, then we're definitely good. So I want Q1 to be in the first set of final states, or the second one to be in the second set of final states. So Q1 is in F1, or Q2 is in F2. So this is the construction that we've seen in class. Oh shoot, I should have told you. I meant to do intersection instead of union. Do I have to do this whole thing again?
No.
Oh, wait, what thing has to change?
Change the word and.
Oh yeah, I only have to change one word if I'm doing intersection instead of union. Okay? Are we good with that? So now let's start doing some examples. So I have 4 on the front. I doubt we'll get to the 4th, but we'll see what happens. On the back, I have 3 additional exercises just purely for you to get some additional practice doing this stuff. But we'll try to do at least the first 3 today. So let's look at this first one. It says that I have a language L, and it's a set of all strings in 0, 1 star, such that the number of occurrences of the symbol 0 is not 2. All right? So I want any string that has 1 occurrence of 0, 0 occurrences of 0, 3, 4, 5, and upward. Just not 2. That's all I don't want to accept. All right. So what is the first thing when you look at this? What is the thing that strikes to you as being somewhat important? What part of this do you think is the most important part? Yeah, this not equals thing, right? That's the thing that we're trying to check. Well, that must mean that this is not true, but it seems like we have to check is equal to 0, also have to check equal to 1, check equal to 3, 4, 5. Are there infinitely many cases to check? So that seems like a problem. It's not, but it seems like a problem, right? So what can I do with this to make this a lot simpler for me, for us? Well, let's see. Can I change this not equal to something else that's easier? Yeah, to what? Equal, right? Oh, what operation is that? Changing not equal to equal. Complement. Oh, am I justified in doing that? Ah, okay. So let's find the complement of this, and then we'll make the DFA for the complement of whatever we make. So let's consider L bar, which is the same thing as 4, but the number of zeros is exactly 2. Okay? So let's make a DFA for this, and then we can make a DFA for the original guy. So how would I make a DFA for this, for exactly equal to 2? Well, let's see. If I've seen 3 zeros, do I care what the rest of the string is? No, right? So I only need to really keep track of seeing exactly 0 zeros, 1 0, 2 zeros, or 3 or more zeros, because after that I don't care. So let's make 4 states. Each one represents how many zeros we've seen. So let's make a state Q0, Q1, Q2, Q3. And we just reasoned that, let's do this first. What should be the start state of this machine? Q0, right? Because if I've seen nothing so far, I've read 0 zeros for sure. So this better be the start state. So what do you think Q0 is going to do on 0? Go to Q1, right? Because if I've seen 0 zeros and then I see 0, then I have seen 1 in total. What about 1 on 2? Oh, sorry, 1 on 0. Goes to Q2, and I bet you see the pattern. Q2 goes to Q3. What do you think Q3 is going to do? Do that looping thing, right? Because once I've seen 3 zeros, I don't care what the rest of the string is. So it's going to loop on 0. What's it going to do on 1? Same thing, yeah, because I don't care what the string is. Good. Am I done? Oh, what have I forgotten?
Final state.
Oh, I forgot the 1 transitions. So what is Q0 going to do on the input 1? It's going to go to Q1 or Q0? Q0. Why does it go to Q0? Or why should it?
The only thing we're tracking with those states is how many zeros we've seen.
These states keep track of the number of zeros that we've seen. If I see a 1, that doesn't change the number of zeros that I've seen. So we're justified in making a self loop there. Oh, wait. What does that tell me about what Q1 and Q2 are going to do on input 1? Same thing, because it doesn't change the number of zeros that I've seen. So these are going to self loop also. Am I done? Oh, what have I forgotten? Final states. So we're doing L bar right now. So what should be the final state or states? 3? It should only be 2, right? Because I only want to check the case where I have 2 zeros that I've seen. And that's the only state where I've seen 2 zeros. So this better be the final state. Okay? But our original problem was the complement of this. So how do I find the DFA for the complement of what we just did? Exactly. Switch the final and non-final states. So if it was final before, make it not final. If it was not final before, make it final now. So this was not final. This is not final. This is final. So make it not final. And this was not final, so make it final. Let's see, one person nodding their head, so therefore everyone understands. Right? Does that seem reasonable? approach? Are there any questions? Because this is the perfect time to be asking questions about the material. No questions? All right, so let's do the second question. So the second question is, I want to recognize when I've seen an even number of zeros and either exactly one or two ones. Okay? So those are the only possible, that's what I want to recognize. So, what word of this jumps out to you? The and. Oh, so what do you think that corresponds to? Yeah, it sounds like intersection, right? Because it has to satisfy this condition and this condition. Oh, so if I can make a DFA for the first part and a DFA for the second part, can I make a DFA for the whole thing? Yeah, that is essentially exactly what we just went through at the beginning. So let's do that. Let's make a DFA for the first one first. So I'm going to call it L1. So it's all the strings in 0, 1 star with number of zeros is even. So how would I do that?
Are we counting 0 as even?
Yeah, number of zeros is even.
Well, so I mean, if we've seen 0 zeros, does that count as even?
The number of occurrences of the character 0 is even. So if it's the string 0, 0, then it's 2, which is even.
Okay, what about if it's an empty set?
What is empty set? You mean empty string?
It's an empty string, yes.
Yeah, so how many instances of the character 0 are in the empty string? 0, which is. So I have two cases. Either the number of zeros is even or it's odd, right? That's one of the techniques I demonstrated last week is if you have a finite number of possibilities, model each one as a state. So the possibilities are even or odd. So let's make each one a state. So let's make a state Q even and a state Q odd. So relating to the question I was just asked, what is the start state?
Even.
Even, because the empty string has even length, so therefore it must be there. What are the final states? Q even, right? Because I want to recognize only the even case. So I better make Q even the final state. So now all I have to figure out is where's everything go on 0 and 1. So where do you think Q even is going to go on 0? I heard odd and even. It better be odd, right? Because if I've seen an odd number of zeros and I read one more, I've now seen an even number. So I better go, the other way around. If I've seen an even number and I read one more, then I have seen now an odd number. If I have seen an even number of zeros and I read a 1, where should I go?
Even.
I should stay even because reading a 1 doesn't change the number of zeros that I've seen. So I should stay in Q even. Oh, silly me. Should be 1. All right, so what do you think Q odd is going to do on 0? Go back to Q even, yeah. So just reading a 0 changes which state I'm in. What do you think odd's going to do on 1? It's going to stay 1 again because if I've seen an odd number of zeros, read a 1, I've still seen an odd number of zeros. So I better loop here on 1. Okay? Cool. So let's do the second one. I'll do it. So the second part is number of ones is exactly 1 or exactly 2. Wait, does that seem a little familiar? At least something close to what we've done before? Oh yeah, it looks somewhat similar to the one we've seen above, the one for L bar, where we had exactly 2. Oh, but it says 0 instead of 1. So what can I do? Could I use something similar to this? Okay, I can swap between zeros and ones. I can switch the role. So instead of having zeros go across the states, I can have ones go across the states and zeros be the self loops now. So again, I'm going to have 4 states. Q0, Q1, Q2, Q3. And then we're going to have ones go across, because I'm now going to be keeping track of the number of ones that I've seen. Q3 is still going to self-loop on everything. And these guys are going to all self-loop on 0. Because they don't change the number of ones that I've seen. Am I done with this second DFA? Oh, I gotta choose final states. So what are going to be the final states of this? Q1 and Q2, because those are the cases that I want to recognize. So I make these two the final states. Okay? Any questions about how we do that? Am I done with this whole problem? Oh, what have I forgotten?
Intersection.
Oh, I gotta do the intersection. The product construction is what it's called. Okay. So, how am I gonna do that? Well, let's think about how we would actually make a DFA for this. How many states is this DFA going to have? Well, remember, I have 2 here and I have 4 here. I'm going to have 8 states. Why? Because I got to have an ordered pair, remember, with even with all 4 of these and odd with all 4 of these. Okay? So I better have 8 states. So the way I'm going to write these is I'm going to have 2 subscripts, one from the first DFA, one from the second DFA. So in my mind, I can think about where they were in the original DFAs. So I'm going to have an even, comma, 0 be a state. Remember these names, names of states don't actually matter, but for us it'll be helpful in this case. So I'm going to make an even 1, 2 even 2, Q even 3. Q odd 0, Q odd 1, Q odd 2, Q odd 3. I think that's 8 states. Okay. So now we got to think about the 4 other pieces. Well, we know the alphabet, so we got one there. What's going to be the start state of this new machine? It's going to be even 0, right? Because I got to look at the start states of the original 2 machines, and I know they're even 0. So this better be the start state. I'm going to leave final states until the very end. So let's think about what the transition function is going to look like for this new DFA. So let's think about where even 0 is going to take me on input 0. So first of all, how do I find out what that state does on 0? Right, I look in the original 2 DFAs, see what happened. Well, I was in even, and where do I go from even on 0? I go to odd. So I'm going to end up somewhere down here in one of those 4 states. But where does Q0 take me on 0? It stays there. It stays in Q0. So in my mind, I'm thinking Q odd 0. Okay? So I'm looking at Q odd 0. Think about where it goes on 1. Where is Q even 0 gonna go on 1? Well, Q even, where did it go on 1? It stays there in Q even. So in my mind, I wrote down even. Now I got to figure out what the other one is. Q0 on 1, where does that go? Goes to Q1. So I'm thinking even 1. Okay? Oh, and I had that state. Okay? Let's do Q odd 0. So where does Q odd 0 take me on input 0? Think, where did odd take me? Took me to even, right? Where did 0 take me on input 0? Where did this guy take me on 0? It stayed there in 0. So I wrote down in my mind even 0. Okay? And that's, so basically I come back here. Let's think about where Q odd 0 goes on input 1. Where does Q odd go on 1? It goes back to itself, so I wrote down odd in my brain. Where does 0 go on 1? Goes to Q1. So I wrote down odd 1. Oh, and I have that state right there. Do you think there's some kind of pattern here? Okay, well, let's think about where the 0 transitions are going to go. What do you think? Oh, let's think about it. If I'm in up here, no matter what happens, if I read 0, I'm going to switch between the states. But that must mean if I read a 0, I'm always going to switch between the 2 rows up here. If I read a 0 in one of these states, what happens? I stay in the same state. So what does that mean? I stay in the same column. So it's going to switch rows, but the same column. So where do you think Q even 1 is going to go on input 0?
Q odd 1.
Q odd 1. It must go to odd, but it stays in the same column. So therefore, it must go to here. Q odd 1 on input 0? What do you think? Q even 1, yeah, because same column, different row. I say this that this won't work in general. You usually don't have a pattern like this, but we actually were able to see a pattern here. What do you think the 2 states are going to do on input 0? Again, they're going to swap back and forth. Yeah, on input 0. Good. What about the 3 states? Same thing, yeah, they're going to swap back and forth on input 0. Am I done? Not even close. So, I forgot the 1 transitions. So, let's figure out where the 1 transitions are going to go. Where's Q even 1 going to go on input 1? Well, it's going to go to 2 because 1 goes to 2 on input 1, but it stays in the same row. All right, so it goes to even 2. Oh, do you see a pattern with the 1s now?
Yeah.
Oh, what's the pattern? Okay, so it's going to traverse across here, but wait, once it hits 3, I'm out of room. Where am I going to go? Ah, it's going to do the self loop, right? Because when I'm in whatever up here, I stay in the same state. But if I reach 3, I'm going to stay in the same state. So no matter what, if I'm in the 3 column, I'm going to stay in the same state on input 1. So Q odd 1, that's going to go over here, odd 1 to Q odd 2. Q even 2 is going to go to 3, even 3. Odd 2 to odd 3, and even 3 to itself on input 1. So it's nice that even with such small DFAs, we can see nice patterns like this. And we were able to recognize it nice and early, so we didn't have to figure it out every single time. Sometimes we do. Sometimes we actually do have to figure it out. But it's nice we're able to do it here. Am I done?
Final stage.
Oh, yeah, final stage. What language is the machine right now? What strings does this machine recognize as is? Does it accept anything? It doesn't accept anything, well, because there are no final states at all. So it can't accept anything. So how do I figure out what the final states are? Oh, well, I think, well, what operation am I doing? And, which is? Intersection. So what kind of states do I want to see?
Where both conditions are met.
Where the first coordinate was even, and the second one is either 1 or 2. Both of those have to be true. So what states are going to be final? Even 1 and even 2. Those are going to be my final states. So even 1 is going to be a final state, even 2 is going to be a final state. Okay? Are we good with that? Somewhat if kind of half raised again.
So like for instance, when the question on the recitation paper says construct DFA, would we draw both? We should draw both of them and then that one.
You can, but if it says construct a DFA, it just means the final result.
So the one with the ordered pairs.
It doesn't. The names aren't important, but for us, it was easy to figure out. Okay, this represented even before. I could call this Fred 1, Fred 2. It doesn't matter.
Oh, okay.
The names aren't important. Any other questions? Yeah. Yes. So I could squash these down to one so-called dead state, right? Because once I'm in either of these states, I'm never going to accept ever anyway. What's the reason not to do that? Well, once I get to the 3s, then I'll never accept anyway. So why would I? It's obvious why I would want to do this because it's a smaller DFA. But what's a reason why I would not want to do this? Well, then that means that I have to introduce figuring out what states can I put together, right? I got to actually think about how am I able actually to do this? Whereas before, all I'm doing is just doing the product of the states. I'm not thinking about, okay, maybe I could put these states together or not, right? So the whole reason to do it this way is because it's algorithmic, okay? And that's actually, when we do a lot of constructions in this class, they're purely based on doing it algorithmically. It's not any kind of intuitiveness or geniusness or whatever.
Efficiency, we don't really care.
Yeah, as long as it's finite, well, we don't care. Efficiency is important, but not at this level. Any other questions? All right, so I think I can kind of start the next one. So the third language that I want to recognize is number of zeros is even, or the number of ones is not a multiple of 3. So what's the word that stands out to you? Well, not, but what's the bigger connective? Or, yeah. So what do you think that corresponds to? It sounds like union now. Okay, well, we know how to do union. It's very similar to intersection. So if I can make a DFA for the first part and the second part, then we can combine them like we did before. What about the first part? Number of zeros is even. Oh, we just did that one, right? So it's really nice that we were able to use one DFA for one problem, and then now we can reuse that DFA for the other problem. So I'm just going to rewrite it here. Number of zeros in W is even. So are we good with this product DFA? Because I'm going to erase it for a very good reason. All right, no objections, so we're good. So I'm going to write it in a kind of weird way, but it'll actually be very useful in some. So this is the language I want, and then I'm just going to copy and paste the DFA over here. So do even. a DFA for the second one. So I want L2, which is all strings, such that number of ones is not a multiple. So can I make a DFA for this? Well, let's figure it out. So if you see a multiple of 3 type question, what do you instantly think we should do? Oh, keep track of the remainder, right? So how many remainders are there with 3? How many remainders?
3.
Just 3, which are 0, 1, and 2. So let's make a state again for each of those possibilities. So I'm going to write them vertically for a reason you'll see in a second. So Q0, Q1, and for the interest of time, I'm not going to do the complement because that would be easier, but I'm not going to do the complement. So what should the start state be for here? It should be Q0 because I haven't read anything, so the number of ones we've seen is 0, which is a multiple of 3. So I should have that be the start state. So now let's figure out where it goes on zeros and 1. So where does Q0 go on 0? Does reading a 0 change the number of ones that we've seen?
No.
No. So what do you think Q0 does on 0? It loops on itself. Good. What do you think Q1 and Q2 then do on input 0? They're also going to loop on 0. And so now what do you think the 1 transitions are going to do? So let's start from the beginning. Q0 on input 1, where does that go?
Q1.
It goes to Q1, good. Where does Q1 go on input 1?
Q2.
Q2, yep, because if I have remainder 1, then I read 1 more, now I have remainder 2. Oh wait, where does Q2 go on input 1?
0.
Goes back to 0 because, wait, shouldn't I go to a Q3? No, because if I have a multiple of 3 and I add 3, now I still have a multiple of 3. So I should come back here. Okay? So in the product DFA, how many states am I going to have? 6. 2 for this DFA, 3 for this DFA. So let's make our states. Q even 0, Q odd 0. So I wrote this one horizontally, this one vertically, purely to see that this is the even column and this is the odd column, and this is the 0 row, 1 row, 2 rows. So we can actually figure out like what states are final and then what the transitions are much more easily this way. So I have a Q even 1, Q odd 1, Q even 2, Q odd 2. All right, what are my final states? Sorry, what's the start state? Q even 0, because this one's start state, this is the start state, so that's the start state. Where does Q even 0 go on 0? Q odd 0, because I know this one will go to the other column, this one stays in the same row. So I go over here on 0. Where does it go on 1? It will stay in the same column because it loops on 1 here. But what state does it go to in the column? It goes to 1 because we see in there it goes down a row. So we come down here. What do you think the 0 transitions then are going to do? It's going to oscillate back and forth like the now erased DFA did. So this one, I hope you can figure out, comes to even 0 from odd 0. If I'm in even 1, I go to odd 1 on 0, even 1 on 0 from odd 1. And same thing for the 2s. Okay? So let's figure out what happens with the 1 transitions. What do you think the 1 transitions are going to do? Well, let's think. What is odd 0 going to do on input 1? It's going to go to odd 1 because 1 here stays in the odd column, but it comes down a row. So it's going to come down here to odd 1. What do you think the 2 stays in the 1 row are going to do on input 1? Say what even 1's going to do. It's going to go down again, right? Because it stays in the same column, but it comes down a row. So it comes down here. And we can see that this one also does this. Odd 1 goes to odd 2. Am I done? Oh, what have I forgotten?
Even to on
Even 2, odd 2. So what are those going to do on input 1?
loop back up.
Again, they stay in the same column, but here with Q2, they go all the way back up to Q0. So these guys are going to come back to their same column, but to the 0 row. So this is the 1, and this is the 1. Now am I done? Oh yeah, I keep forgetting those staying final states, right? All right, well, again, what operation are we doing? Or, which is union, right? Okay, so I gotta figure out what states are gonna be in the union, right? So how would I figure that out? Okay, well that must mean that the first coordinate is even. All the states that have first coordinate even are gonna be final. Oh, we actually didn't do final states of this one. So what are the final states of this one? Q1 and Q2. Sorry about that. But notice the important thing. I didn't need that information until now, right? So I can wait until the very end to decide, am I going to do union or intersection? So anything with even is going to be a final state because it's the union. Anything with even. But are any other states going to be final? Yeah, anything with 1 as the second one is going to be a final state, as well as anything with 2 in the subscript is going to be a final state. So this one's going to be a final state, and this one's going to be a final state. Okay? Any questions on how I was able to do that? Okay, so we don't have enough time to do the last example, unfortunately, but I'm gonna motivate it a little bit. So suppose I change this problem to be very similar to the 4th question, which is instead of doing just or, I put but not both as a condition there. So I don't want both conditions to happen at the same time. So how would I modify this? Would I need to do this whole thing again? I don't think so. So what thing am I going to change? The set of final states, right. So what final states are going to change then? Okay, I'm going to remove from the set of final states the ones that would have been the intersection. So what are the ones that would have been the intersection? It's the ones that have even and 1, or even and 2. So I'm going to remove those as the final states. So the other final states represent exactly one of the 2 conditions that's satisfied. Okay? Any questions about any of this? All right, I'll see you next week.